Alright, normally I don't do a video like this. I'm going to apologize for the noise. Normally I wouldn't have an air conditioner set up blowing out my front door, but I'm waiting to hear back on when they can come replace my air conditioner. It's been a long weekend, we'll put it that way, between the air conditioner and the wasp nest in the chimney. But anyways, so I'm going to reply to JM the Pilot on TikTok. And normally I wouldn't make reply videos, but I kind of trolled him into some stuff. So I feel like I should give some context. I was trolling him because he had left out some context. Now, to be fair, 1-minute videos are not a great way to include context. I don't know if he has 3 and 10-minute videos available to him. I don't care, because more than likely, if he went like I'm gonna do and go through a bunch of stuff, people aren't gonna wait through the first minute anyways. So anyways, this is more for his sake, and maybe if some people want to see what I was kind of trolling about. This is the video that started it all. I left a comment on it that was accurate, and I got a lot of hate for it. I think because people are just that tribalistic, more than just politics. You get into the car space, it's pretty bad. So here we go.
Fully charged Ford F-150 Lightning has less energy on board than a regular F-150 with 4 gallons of gas.
This is not the gotcha the anti-EV would have you believe. It's not saying that an internal combustion Ford F-150 with 4 gallons on board is going to do the same amount of work as a fully charged Lightning. All that number really means is that 131 kilowatt hours, which is the battery size of an F-150 Lightning, contains about the same amount of energy as 3.5 to 3.7 gallons of gas.
Okay, so remember those numbers, 3.5 and 3.7. I kind of took the worst case scenario, 3.7. Battery activity varies with temperature too, and he doesn't talk about that at all. Particularly if you live in a climate like I do, where in the winter we see 30 below, and in the summer we see 105. That is a pretty typical range for us. We can push outside of it. Up here in North Dakota, we hold the record. I do believe it's for North America, but for the United States, for the largest temperature swing in one year, it was negative 60 to 122. That is a 180 degree temperature swing, okay? It was back during the Dust Bowl. So there's a lot of records from back then that probably won't be broken for a while. Moisture, even a little bit in the soil, helps temper those extremes a little bit. So 3.7, 3.5. I'm going to use 3.7 because I'm going to give the electric all the advantages. Because he left out some context that even with all the disadvantages, still put it ahead for the average person. Okay?
Depending on temperature and pressure. Remember that the reason internal combustion cars even carry all that extra energy with them is because they're demonstrably inefficient. 70 to 80% of the fuel that you put in that gas tank is just going to radiate out into the atmosphere as heat.
That is also kind of false. 20% is a really, really low number. That's going to be talking more along the lines of carbureted big blocks than it is a modern direct injected motor. Modern direct injected motor, you're going to see more than 30% on it. Again, he's making generalizations about something you could see on the road, right? The range you'd see on the road. I don't quite like that because we're comparing a brand new electric truck against stuff that's basically anywhere from 10 to 40 years old. And in the last 10 years, we've seen quite a bit of new technology implemented in motors. So, actually, even the last 15, to be honest. I don't really like doing that. I like comparing it against brand new to brand new. Because that would be almost like going to the NiCad battery from the 90s, you know? If you really want to start getting into comparing old technology. Okay.
Meanwhile, the Lightning can turn almost 95% of that battery power into locomotion.
Okay, so the Lightning, he says 90 to 95% of battery power will go into locomotion. Missing context here. That is only if that's what you're using it for. All right. That's the efficiency of the electric motor. That is not the efficiency of the truck. We're going to make that distinction very soon here, because he's going to use a clip in his reply video that exemplifies this. And I don't know if he quite understands that that's what's being exemplified. But anyways, let's keep going.
Where do you think that electricity comes from?
This made me laugh because I live in a state that has a lot of coal. And you hear this a lot. In fact, I'm laughing kind of hard. Sorry. One of the cooperatives that runs a lot of the coal up here is the company with the Teslas, okay? Which makes sense because they're using their own product, right? I just found this kind of funny because he goes on to make some valid points here. Let's continue.
Well, if you've been watching my videos, like this one right here, remember how I talked about how efficient one of these gas turbines is? Because the efficiency gains in centralized power production, even when that power comes from fossil fuels, means that we reduce our production of CO2, we reduce our dependency on foreign oil, and we're able to scrub emissions at a central location. To me, this doesn't say electric truck fail, it says electric truck win.
Okay, so some of this is a win, some of it's a fail. Like everything, there's pros and cons. Let's go down to the comment that started it all. So an average truck tank is about 30 gallons, 30 to 35% efficiency at this energy. We're talking new stuff here. You know, you've got some motors that are running turbos. That helps recycle some of the energy back into the system. You've got variable cam timing, so we can run the peak torque at various throttle positions. The pedal on the floor is no longer a direct correlation to your throttle opening. Okay? That is telling a computer kind of what power you want, and then the computer's optimizing that motor for you. It's changing your cam timing, it's opening the throttle just to the right position. If it's optimizing your spark timing, if you got turbos, it's doing that. A lot of stuff going on there. It's more of a power demand instead of a power production pedal, if that makes any sense. The computer does the production and you tell it how much power you want, and it does it to the most efficient it can. It's going to select the right transmission gear. Now that we're getting these 8 and 10 speed transmissions over the last 10 years, that's really important. But the transmissions aren't that important when we're talking about just the efficiency of the motor, okay? That's an inefficiency of the truck itself. So here's the comment right here. Average truck, about 30 gallons. And let's see, I don't have that link pulled up. Let me pull it up. Okay, I found the link. So this is pretty standard, 23, 26 gallons. Most of the packages on these trucks are coming with, and these are half tons, okay? This is a F-150 and a Ram 1500. GM is very similar. Mid-20s is what you're gonna find as the standard tank. And then you can see some of these packages. We got 33 gallons. Let's see, where over here on the Ford, 36 you can get on a Raptor, okay? And these are just the tanks that are standard for these packages. A lot of the times you can order the big tank as well. When I was working at the Dodge dealership, a lot of the crew cab trucks, particularly the higher end ones, or I shouldn't even say high end, mid trim, the big horn on up, you saw optioned up from the factory with the bigger 32 gallon tank. So why is that important? Because here I said you get an average about 30 gallons. Okay, so we went at 30% efficiency. That's 2.2 times the usable energy. So let's do some math here, why don't we? So we've got 30% times your smaller 26 gallon tank most of these trucks come with. And if we have one charge, 3.27 gallons worth, that comes out to 2.1 charges at 30% efficiency and 1.4 charges worth at 20% efficiency. So this system kind of at its worst, neglecting the loss you get in your electric drive motors, even because if you took these numbers times 0.9, you'd divided by 0.9, you'd obviously get a much larger number. I'd have to do that quick here. You're probably looking at like 1.6 and 2.4-ish, right? Okay. So And then I said something along the lines of diesels are even more efficient. And then somebody was like, no. And I just kind of went off the rails at this point. I was claiming 50, 65%. That's 65% isn't even the most, that's way above even the most optimistic numbers for the end of the decade, okay? That's a way above that even. So anyways, that's a troll. But that troll got this next response here. Okay, so let's look at this. Now, I said 45 to 55% in the engineering literature. That's exaggerated, but not that exaggerated. Now, I've got a study here that'll talk about that in a second, but we're gonna go through what his, yeah, we have high pressure injection, right? So I did mention that already. Let's get going here.
This comment right here says that most of these engines are between 45 and 50%, and I need to get educated. Let's go to school, shall we? Let me introduce to you the Rostila 31. And according to Guinness, this is the most efficient 4-stroke diesel engine in...
Okay. June 2nd, 2015. Chances are this may not have even been the world record at the time, because, you know, you have to apply for those. I'll give it that it was, even if it wasn't, it was right there. I mean, somebody might have been able to beat him by a couple tenths of a percent, right? But the fact of the matter is it's still a 7-year-old record, and with the way technology has been progressing since 2000, I don't consider that even viable. Somebody's beat that already. They just haven't applied for the record.
in the world. How efficient is that, you ask? 48%. Of course, this efficiency is at one specific RPM, fuel flow, and load.
Okay, he mentions this, and I would like you guys to hold on to that thought for a second, because we're going to talk about a little bit of motor theory here, because this 1 RPM thing isn't quite as accurate as he keeps saying.
And that we'll talk about in a second. As it turns out, getting diesels above 40% efficiency is really hard. Getting them above 50% is damn near impossible. In fact, about 15 years ago, the Department of Energy, in conjunction with Caterpillar, they...
So he says about 15 years ago, right? If you look on here, does he show it on here? I went and looked up the document. This was published, oh, there it is. Completed December 2006. Okay, so 16 years ago.
Conducted a study to see the feasibility of diesel motors over 50% efficiency. Through computer modeling, they were able to come up with a proof of concept that was just a smidge above 50% efficiency.
Okay, context. 2005 is when they completed this study. Again, we're just scratching the surface with high pressure injection. Variable geometry turbos have been put widely into usage since then, and injection pressures are way higher than they were back then. We'll talk about that in a second.
Their opinion was that thermal efficiencies above 50% in commercial applications were just unviable. Not currently, anyway. If you take a look at what's available on the market right now, like this Caterpillar 3408 that's running in a lot of older trucks, its efficiency is...
That motor's not available anymore. You got to find them used. They were discontinued in 1985, and this actually pissed me off. That you would take an example that old, something that was discontinued in 1985. Think about that for a second. That's that motor is discontinued 37 years ago. And this really amplified my trolling quite a bit. Not gonna lie, when he made this reply video like this. There's been so much done to these motors since then, it's unbelievable. And it has increased the thermal efficiency a bit, but what it has done for emissions is unbelievable. They are so much cleaner today than they were back then. And I kind of trolled him a little bit by saying, well, why didn't you pick like a 3306? Because a 3406 is a 3408 was a heavy haul motor. He deleted the video that he replied to that comment, by the way. Probably because that's where I admitted I was trolling. 3306 is almost exactly the same thermal efficiency. They were built and developed at the same time. It's a 34 series, which means it's going to have the same displacement per cylinder. You're going to be sharing pistons, liners, injectors, all that kind of stuff, just a different configuration. The 3406 was an inline six, and the 3408 was a V8. 3406s were like a 14.6 liter, and the 3408, I'd have to go look it up, or maybe it was in his video here in his spec sheet.
The 3408 that's running in a lot of older trucks.
Yeah, 18 liter. It was a heavy haul motor back in the day. So that's the way you had to get things done, make them big. Diesels used to be less than 1 horsepower per cubic inch was considered reliable. Now they're a little bit above that. This would have been one of those motors that less than 1 horsepower per cubic inch is where it would have been reliable. So anyways, let's continue here.
Its efficiency is about 38% at a specific RPM, fuel flow, and load. And if you look at a super modern diesel like this Cummins X12, its efficiency hovers right around 42%.
Which isn't great, but it's a lot better with current context. So we're going to talk about current context versus a 3408 in a second.
At 1 RPM, 1 fuel flow, 1 load. Why do I keep saying that? Well, Chase from Edison Motors, take it away.
Here's what it looks like. Watch as I'm shifting gears. I spend a lot of time in neutral, and every time I shift, you can hear that engine lug down, and then that turbine spools up. It just gets going when I have to grab another gear again and do it all over.
Between accelerating, idling, and decelerating, modern diesels are only running at 20 to 30% efficiency. Now, in contrast, the Department of Energy has also conducted studies looking at the effects of load and efficiency on electric motors. And what they found was that under almost every load, whether it's high or low, high power motors are mostly above 90% efficiency. And electric motors waste very little energy while braking. In fact, most regenerative braking systems recover about 70% of kinetic energy. So I like to think I'm pretty well educated on this stuff. Guys, let me know if you have any other questions.
Okay, so that's the end of the video. A lot of irony in what he was just saying about Chase from Edison Motors. And obviously he likes Chase. I love Chase. He's doing something I said should have been done like 10 years ago. I started talking about this. Chase at Edison Motors is basically making a road-going locomotive. So most of you, or maybe not most of you, trains are giant diesel generators that run electric drive motors. It is just not feasible to make gearboxes and try and transfer through shafts all of the torque required to get a freight train or a passenger train or any kind of train moving. All right, and they never did. They went straight from, well, pretty much straight from coal producing steam to diesels producing electricity. And that's exactly what Chase is doing. He's taking a diesel motor, he's putting it right in that peak torque range. It's smaller, so it's not going to use quite as much fuel. And he's taking the inefficiency of the truck out of the equation. Okay, we're back. I ended up getting a phone call in the middle of that. Anyway, I was talking about, he's using a clip of Chase talking about inefficiently the truck is using an efficient motor. That's the irony of it to me. I've seen the clip. The clip's old. I'd have to dig through Edison Motors' page. God, that's probably a year old already at this point. In fact, me and a couple friends have talked about doing a similar thing with a car, because 90s GM cars are, you know, a few $100s with a blown motor. But anyways, he's talking about taking the highest energy density fuel we have available to us, that's the cheapest, and using it in the most efficient way possible. The inefficiency of a truck or a car or whatever behind the motor, it doesn't care what motor's in front of it, that inefficiency is going to be there. That's why I don't like this argument that they like to make. Now granted, you typically don't see electric motors in front of gearboxes, particularly gearboxes that are 13, 18, maybe even 21 speeds. I've seen some of these heavy haul guys have a 18 speed transmission that's also got a 4 range selector on the back side of it. So yeah, 84 possible ratios they could be choosing from. Now a lot of them are impractically close to each other when at low speeds, but anyways, I digress. He keeps saying this 1 RPM thing Now, one thing you need to know about internal combustion motors is peak thermal efficiency. You're getting the most work for the amount of fuel coming in is at peak torque. Peak torque is peak cylinder pressure. Let's take a look at this DD13. And you see this on a lot of modern trucks when they've published the dyno charts. Peak torque is actually an RPM range. So there's probably a point here where it's the best, but this line is pretty flat. And we're looking at all the way down from just under 900 RPM to just under 1500 RPM. So a 600 RPM swing, which is less than your typical gear split on a truck is where you're operating your peak efficiency, which makes sense. You're going to design this motor to work as the best way possible with what it's going into, right? And you know that it's going to be operating somewhere in this range, and it doesn't really matter if it's in a truck, if it's in a generator, if it's driving a hydraulic pump, you're going to be operating here, okay? Except maybe your warm-up idle time, because this 900 is going to be about where high idle would be on a lot of them. All right, so let's take a look at this. We have the International Council on Clean Transportation, the ever-improving efficiency of diesel motors, or diesel engine. Yeah, okay, so I go through a little history here in the 1880s. Really, the first ones weren't developed till around, he didn't really have them running on their own until 1897. Injection timing and that stuff was very poorly controlled. And because of that, yeah, 26%. So they've come a ways. We have different tiers of diesels nowadays. But here's the important thing. 2013 to 14 compliant motors, or certified engines, are down here with this 43 to 44%. So most of the stuff you're going to be seeing in large fleets today is going to be 43, 44%. We're looking at 9-15% reduction, right? So bottom line, by the end of the decade here, to surmise this, we are looking a little over 50%. We're like over 10% from a 2017 baseline. So when you pulled up that study that was that old, this is how outdated that study is, right? They're looking at over 50% by the end of the decade. Cummins, Daimler, Navistar, we're looking at 50, 51%. Now their follow-up goal is going to be 55%. That's pretty good. And people are wondering why there's so much effort being put into this. It's because trucks take a lot of energy to move that cargo through the air. Even the ultra sleek trucks, it's a lot of frontal area on the trailers, all right? Which is one of the reasons why Tesla's kind of insisting on redesigning everything. So let's take a look at what does that mean compared to batteries. So here we go. U.S. Department of Energy, you seem to like them. I seem to like them. So gasoline is what they have as their standard. That gasoline and 1 gallon of gas contains about 97 to 100% the energy of gasoline. The reason there's a little range on that is because this is 10% ethanol, so it actually is a little bit lower than pure gas, but it's close enough for what we're going to talk about. Diesel, 113% that of gasoline. Batteries, 15.3%. This is why it's not very viable in commercial applications currently. If that battery number improves, like doubles, I can see a lot of use in this, all right? Okay, so we already went through this example here, the 26 gallons. Let's go straight to the percentage here. So we've already demonstrated that diesel trucks, 40% is not unrealistic. Let's say 30% because it's a Swift driver, and that's an inside joke for the industry. Swift drivers are not regarded as the best. I'm sorry if you're a Swift driver and watching this and you're good. I'm sure there's some of them out there. Takes one moron to wreck a whole group, right? So at 40%, we're going to standardize it to the same as gasoline, since they don't give the diesel equivalent here. They give it up here, right? So the smaller this number, so 1 kilowatt hour is equal to that smaller number of diesel that is gasoline. All right, so we're going to standardize this for percentages. A 40% efficient diesel motor would be making about 45% efficient if it's a gas motor. We're going to divide that, assuming we're getting 100% transmittance from that battery to the ground. We're looking at almost 3 times the amount of usable energy. If we drop all the way down to 30%, which some you might claim is more realistic, and in some cases it is, some cases it isn't. So that's 33. That's still over twice as much usable energy. This is why I find both sides of this infuriating, is because they blow everything out of proportion. Although this is not insignificant. Got a quick story. On a way to a funeral last spring, pulling a car because it was significant to the person who died, in a car trailer with my brother's diesel truck. It was about 24 degrees when we left that morning. 35 mile an hour sustained headwind. And I see you're a pilot, so you can appreciate this, how wind resistance affects things, with 50 to 60 mile an hour gusts. That truck barely made it. It was 100 miles between when we left, got to the funeral, and got to the gas station. 26-gallon tank, he barely made it. That Rivian that you have, chances are, would not have made it looking at these numbers. Not even close. And you would have barely made it to the next gas station that was like 50 miles away. Well, there's one at about... Anyways, pick back up where I was at. You would not have made it with that Rivian. There's no charging stations in between Bismarck, where I live, and Dickinson, where that funeral was. Is this a normal circumstance for people? No, not at all. At least for most of the country. Something else I'd mentioned earlier, battery activity goes down in the cold. Yeah. Heaters. Oh my God. So when you're talking about using the thermal energy produced, internal combustion motor, when you turn your heater on, there's a little bit of electricity driving the blower motor, but it's using what normally would be radiated off to the environment to heat the cabin. That's not the case with a battery-powered vehicle, because there is no excess heat like that. The batteries don't get that. They don't let them get that hot. So the cooling system on the battery is not a viable option for heating the passenger compartment. So you have to directly heat it. And yeah, electric heaters draw a lot of energy. You think about a standard bathroom heater that's like 1800 watts to run. That's not going to keep you comfortable when it's 10 below. I've tried. I had a truck that had a heater issue. I had an 1800 watt inverter in it, and I tried a 1300 watt. It could, just sitting still, it could barely warm the cabin 30 degrees above ambient, and that was at 10 degrees. So you're talking about a lot of wattage, and that's all coming out of the battery. That's not being used for motion. Same with air conditioning. The rotating energy of that motor is going to drive that compressor really easily. It's not drawing that much. But when the electric motor for that compressor has to run just like your house, that's a lot of electrical draw. So the sweet range for electric vehicles, at least the people I've talked to that own them, seem to be about 50 to 80 degrees. Outside of that, you're having to drive a lot of just your climate control and stuff. It's a pain, and it cuts your range. Most of the people I talk to that live here in Bismarck, because there's quite a few Teslas in Bismarck, you start talking to people and their range is cut in half in the wintertime driving around town versus driving around town in the summertime. So the spring and fall is the best time. So anyways, this is my reply to JM the pilot. Actually, I'm not quite done yet. Let's talk about, just briefly, this dyno chart for that DD13. This flat area up here is because of technology that has now come into effect since that first study you did. You got your variable geometry turbos, you got your injection timing is all electronically controlled. We're pushing injection pressures upwards of almost 50,000 PSI now, whereas those old mechanical injected motors were maybe a few thousand. All this being controlled in sync allows you to have constant cylinder pressure, and that's how you're building the same torque across that RPM range. You can vary the boost, you can vary the fuel, and you can keep that cylinder pressure the same, which is where you're getting that similar efficiency. So anyways, I love Chase. I don't know if you're purposefully taking things out of context. Maybe you just didn't quite know, but yeah, sorry, I trolled you at that 3408 versus 3406 just to kind of see where you're at. And lo and behold, two motors, they're basically the same with one with 2 extra cylinders would be about the same efficiency. So anyways, hope you guys have enjoyed this. There's a lot more to this. It's just, could sit and do like a 5-hour lecture on this. But anyways, have a great day.